So we will be talking about we'll finish just a little bit more on water. I have 12 slides on the water and also how air affects the surface of the earth. And then we'll go into, you could tell that I started on the wrong slide anyway. Then we'll go into talking about geologic time. Now, as the screen's coming up, when we talk about geologic time, it can be uncomfortable. Many of us are creationists, and among creationists, there's a large group that believes that the time between the creation of the earth and now is around 6,000 years. And that's not what scientists, yes, I have more of these now. That's not what scientists believe, and so we'll talk about the way science believes it. And because this class is not, a full-on geology class, we don't really have time to talk about the differences in interpreting data between scientists and creationists. But just keep in mind, I do expect you to understand the scientific interpretations, understand what the data is and how it's interpreted. I don't expect you to necessarily believe that the scientific interpretation is the correct interpretation. It's the best one that scientists have coming from their worldview. I will have a slide where I talk about uniformitarianism, which helps, and I'll talk about their worldview a little there. Okay, so finishing up with water and such, we talked about meanders. Meanders are these streams that, you have a waterfall here and it's just going down a rough valley. But as it erodes, it starts to work its way back and forth into the valley. You notice it eroded away the waterfall, so the waterfall is missing in the intermediate one because erosion has taken it out. And you finally make this valley that is filled with sediment. All of this is sediment from when the stream was covering that area of the valley. As the stream meandered back and forth, it would leave sediment as the direction it was moving away from and fill in the valley. A delta is a place where you have a stream suddenly coming to a stop in something like either a lake or more commonly an ocean. So we have, the Mississippi Delta, famous delta, where you have the Mississippi River comes and meets the ocean. So you have all of the load, as we call it, all of the sand and silt and whatever is being carried by the stream. When the stream meets the ocean, the speed slows down to virtually stop, and that material settles out. And so you have a large amount of deposition that's depositing material. And notice that the deposition is graded. That is, the sizes vary with how far you are. Because when it slows down, the first things to fall out are the heavy things, the things that are big chunks. So when it slows down, the first stuff you drop is the sand, the bigger particles. So you have a sandbar. And if you go out farther, you start getting silt. Silt is a finer grain, smaller particles than sand. And you keep going and you get to clay is actually just compressed mud. And so you have clays and muds out there at the end because it's the finest size material. So you have that natural grading as it slows down. The slower the speed, the smaller the pieces are, the sediment out. So you have a separation. Now, our first of a few clicker questions right here, well, a couple right here. This picture shows an example of what type of geologic feature. Is it a floodplain, a delta, a turbulent flow, or rapids? So let me outline. We're looking at this region here, primarily. The white thing is a stream, yes. What would you name that stream?
It's really interesting how it didn't just go straight through and still has a leak.
Right. Why would it have? What do we call it when it has all those loops? It's a meander. Okay. Still waiting for Maggie and Maggie. Oh, and Brittany. Oh, Brittany, not here. No luck. Okay. 10, 1, 2, 2. So 10 people said floodplain, going specifically to Maggie, who didn't get a chance to answer. I give you a chance to show what you would have answered. Okay, and why?
Because turbulent flow is like faster, so it would be more wide.
Okay, it actually works the opposite. If it's faster, and I wanted to have this here so I could actually talk about that a little more. If the water goes fast, it's not going to make this turn here very easily. Instead, it's going to punch through and go like that. And so that's going to leave this portion out here isolated, no longer part of the stream because it got punched through. We call a stream like this a meander because it meanders through the floodplain. The 10 people correctly answered that. It just moves back and forth, and when you have a flood situation, it will reset its course. It'll probably end up going something. Okay, got to change back, my mistake. It'll probably end up going something like cutting off a lot of things when you have a flood. Clearly, it's going to come something like this and cut off that piece. And that's what leaves your oxbow lakes, such as Lake Carter out there where the airport is in Omaha. Do you have a question?
Are the other ones present somewhere else in that thing?
Not in this picture, no. Turbulent flow and rapids actually go together. Rapids is where the water is moving rapidly, and you usually have turbulent flow in those situations. And delta, well, that's what we just talked about. A second clicker question, which you can answer starting now. This picture shows an example of what geological feature. So the green here is a stream, and then the black is an ocean. Because you can't really tell based on this picture, this is using a clearly false color. Oh no, Mr. Bell. Oh no. Hey, you like this time, Maggie? You're still locked out.
Still struggling.
Okay. All right. Well, we had 1 for everything except for Delta, which had 13. So, Brandon, what's your answer here? And give us your reason why, of course.
I chose Delta because we talked about how a delta was where a moving body of water meets us, like a still body of water.
Mm-hmm.
And so it looks like the stream is meeting the ocean.
Okay.
The ocean isn't moving. So.
That's great. Another thing to help us identify the delta is it's named for the shape. The Greek letter delta is a triangle. Now, that's not a perfect triangle. Of course, you have to look at it from the right direction to make it look like the letter delta, but that's where it gets the name, is from its shape. Your reasoning was absolutely correct. Don't want you to think that my additional information is saying it wasn't. That's an additional way to help you identify it. Okay, glaciers. Yosemite National Park is one of the places that's really dear to my heart. Yosemite National Park was carved out by glacier action. And so glaciers, everybody knows glaciers are ice, right? How many people have been, stood on a glacier? Jackie and me. Pretty cool, isn't it? What color are they? They're like blue, like similar in color to Maggie's bag, which is totally awesome. Those glaciers are big chunks of flowing ice. Now, I said flowing ice. There are two types of glaciers. You have, the two types it has here is not the two types I was going to go with. You have some glaciers that are fixed in place and some that are moving is what I was going to go with. This here, alpine glaciers versus continental glaciers, is talking about the location. And of course, the flow, how quickly they flow depends on it. What defines a glacier? A glacier is defined as a permanent ice body, one that doesn't melt during the summer. So if you have something like, you live here, well, let's not say here in Nebraska because we hardly had any snow this winter. Let's say you live up in Minnesota.
We hardly had snow.
What'd you say?
We hardly had snow.
This year, yeah.
I guess I'm from California. This seems like a lot of snow to me.
No, this year was a very light snow. But like Minnesota, you'll have heavy snow on the ground for half the year, but it melts and it's not there for the other half of the year, so it's not a glacier. But if you have snow that stays there year after year after year, then it's a glacier. And of course, when you have new snow on the old snow, it compacts it. You have air in your snow, right? When you compact that stuff, you form ice, but the air gets trapped in there. So I tried to save a piece of the glacier ice to bring home with me. Of course, you put it in the freezer to try to keep it frozen, but then you have to travel from Alaska to California. And yeah, it didn't survive that trip. But it's very cool because the glacial ice, if you look at it in one direction, you see here's the ice and there's a whole bunch of circles everywhere for air bubbles that have been frozen in. And if you look at it from 9-degree angle difference, you got nothing. It looks clear. How does that work out? What do you think makes it so you have lots of bubbles you see when you look one direction and none when you look at from 9 degrees? So if I look from this angle, I see lots of bubbles. From this angle, I see none. The what? That is a good idea, but it's not the correct answer, right? That would explain it. They're going throughout is the actuality. So if you split it, you'd see them the top half and the bottom half. So what would be another idea? We're scientists here. We have a scientific method. We observe something interesting and we see bubbles from one angle and not from another. Next step is we come up with a hypothesis. That's what we're looking for now. Hypothesis about what would make this happen.
What?
What did I just say about what happens with the glaciers? You have more snow falls on it. What happens? It gets compressed. So because it's getting compressed, a very reasonable explanation is that those air bubbles are not shaped like spheres. They've been flattened out so they're shaped like pancakes. So when you look at it side on, you just have these, little pancake things you don't even see. But you look at it from the top and you see the big circles for the pancakes. And of course, the next thing you'd have to do is to do an experiment. So an experiment might be to try to, cleave the ice and see if you can find these circles And the experimentation shows, yes, that's exactly what it is, that you have flattened out those air bubbles. Because you have flow of the ice. Now, most people think of ice as a solid, right? But that doesn't mean that it can't flex and stretch and flow. So the ice flows, but the part that's touching the ground, of course, is meeting resistance from the ground. And so you have the actual rate of the flow is slowest where it's touching the ground because of the friction there. And increases as you go high. So if you were to drill a straight hole from the top of the glacier down, so that's what this is indicating, a straight hole being drilled from the top of the glacier to the ground, and then you wait some time, the bottom has only moved a small amount while the top part has moved a large amount. And so you end up with a separation. That straight hole would no longer be straight at all, because we call it a differential flow rate, a different rate of flow. Now you notice the last portion here was pretty much a straight line because you have this top section traveling pretty close to constant speed. We call this motion plastic deformation. Plastic because it deforms and doesn't bounce back. It's elastic if it deforms and returns the way it was. So we have this plastic deformation in the glaciers. And of course, you're going to develop, because of this, cracks. And those cracks will have water flowing through them. You know, you have meltwater during the summer, and so you have meltwater going through cracks, making the cracks bigger. So you end up having streams that will run through the glaciers, which is really cool. Actually very cold, I suppose, if you were to get into that water, because what temperature do you suppose that water is going to be? Not warm is pretty good. What'd you say? It's not going to be below freezing, or it would be ice, but it's got to be pretty darn close to freezing, or else you'd have the rest of the ice melting. So it's pretty much, freezing temperature water. And so, yeah, you wouldn't want to hang out in that water. When it says basal sliding, that means the base is sliding. Get it? Basal, base? It's really tricky the way we come up with these terms. Now, glaciers can increase in mass and decrease in mass. You can have an advancing glacier, one that's moving forward, so the end of the glacier is each year farther along. Or you can have a receding glacier. Each year the glacier's end has moved back. Now, a receding glacier does not mean the glacier is sliding backward. Right? That would be kind of funny to have the glacier slide up the hill. If you have a receding glacier, it just means that the rate at which ablation, the loss of ice at the end, is faster than the rate at which it's moving forward. So in this picture, it's showing regions of accumulation. That's going to be up in the mountains where it's cold and you have snowfall. And then regions where you have ablation. Sublimation is the term we use for going directly from ice into air. You would also have melting, going from ice to water, and calving, like giving a cow having a calf, where it breaks off chunks of ice. So these chunks of ice are the results of calving, and the water is from melting. So when you get to warmer regions, you're in the ablation zone. So one glacier that you might have seen, I've walked on 2 glaciers and been to 3. The Mendenhall Glacier in Juneau is the one I haven't walked on. But that Mendenhall Glacier, it used to come like all the way to Juneau, I think. And now it's miles back. It's been receding. And so we look at that and we say, oh no, the rate of ablation is faster than the rate of accumulation. A clear interpretation. But then we have, what causes that? What's the easy answer?
Global warming.
Global warming is the easy answer. And as a generality, I think it's true. A general increase in temperature has caused you to have more sublimation and more melting, and thus the receding glaciers. the first time I looked at a glacier, I looked at this, and you know what I thought I was seeing here? I thought maybe they had gone out there and put gravel on the glacier so that they could drive up the glacier and, have sure traction. Well, that was dumb of me. I didn't know what I was thinking. All right, I was naive. That's not man-made. That's not a road, even though it looks like a road. What this is called moraine. Moraine. I think that's how it's spelled. Not moraine, like moraine. Okay, so moraine is stuff that was ground off the edges of mountains and rocks and stuff as the glacier rolled by. Well, how do you have that in the middle of the glacier if it was rubbed off of the mountains as it came by? Kind of. I'll go with that. If you look in this picture, you can clearly see we have glacier that comes this way, glacier that comes this way, glacier that comes this way. Where they meet, you have the moraine that was on the edge of one and the moraine that was on the edge of the other joins together, giving us the moraine there that's now central to the glacier. And so each one of these tells us that's where we've had material from the edge of a glacier, come together. So in looking at that moraine, you have, there's terminal moraine and lateral moraine. That's the lateral moraine. What's this picture here? Yes, near and dear to my heart, like I said. You have the beautiful falls, big rock monoliths. This here is the Captain, and is the largest single monolith, I believe, in the world. That is the biggest single rock that we know of in the world. It's a big chunk of granite. Where's granite come from? Comes from, I think you said it right, Brittany, but I couldn't hear you clearly. You have a magma chamber that's down low elevation. It slowly cools over millions of years. Because it cools so slowly, you have crystals of reasonable size that grow. That's traditionally how we identify the granite. Not traditionally, it's exactly how we identify granite, by the size of the crystals. And so because it cooled very slowly, you have crystals that might be, 2 or 3 millimeters in length, very distinguishable, that have developed. And so you look at it and you see lots of different crystals in it. And because it's lower density, it floats up to the surface. Now, of course, there's the most iconic thing in Yosemite, the half dome. How'd the half dome form into a dome? Right, we have Half Dome, Yosemite, I think there's Yosemite Dome, and Merced Dome. There's lots of domes in Yosemite. How do these domes form? I haven't talked about this, so this is speculation.
Did something slide down from it?
It does have things slide down from it. These started off as, big chunks of rock. They got to the surface. When they were below ground, they had what we call an overload. A load of soil above that was pushing down on the rock. When it gets up to the surface, you no longer have that overload, and you have what we call exfoliation. You have that granite goes pling and breaks free because it's been compressed, and now it's uncompressed and expands. And so you have the top layers break free, and then when they break free, of course, they slide off. And as this process goes on, it makes the dome shapes. And so it's a natural process of having rock falling near these granitic things because you're constantly having exfoliation. Now, I say constantly having. It's not like it's going spring, 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 spring. But just periodically, you'll have something break free and slide down. And so that's how these are made. Now, if you look at Yosemite National Park, it doesn't look like a river valley. What does a river valley shape generally look like? Like a V. But this here has a smoother shape. The valleys that are carved by glaciers tend to have a U shape rather than a V shape. Why? The water is doing its erosion where the water is running, and it just drills down, making the V shape. Whereas the glacier is this spread out chunk that clears through the valley and carves out the U with it. So you have lots of forms you see in glacial valleys, but what I want you to know is you have that U shape. And these are just places that have been formed under glacier action. You know, pretty much the beautiful places in life that aren't called oceans are glacier places in my view. Okay, now some of the features left behind. I mentioned Minnesota earlier. Minnesota, known as the land of how many lakes? Land of 10,000 lakes. Where those lakes come from? They're what's left behind from glaciers. They're carved out by glaciers. So some of the things you see with glaciers, here we have terminal moraine. You can see I spelled moraine right. Terminal moraine, if you have a glacier that's advancing, it's kind of like a bulldozer pushing soil in front of it. And so the soil that's pushing in front of it, we call the terminal moraine. If it starts retreating, then that stuff that got bulldozed forward is left by itself without any ice backing it, and that's the terminal moraine that's shown there. So that's one feature you see. You have kettle lakes. That's what they have up there in Minnesota. You also have eskers, which are these places where you had a stream running underneath the glacier. And you have these drumlins, which are shaped kind of like teardrops. And I have a better picture of a drumlin here. Oh, no, I don't have a better picture of a drumlin. I thought I did. Well, if you look at these drumlins, you'll see they're like teardrops with the pointy end acting like an arrow saying, this is the direction that the glacier was traveling. So when you look at one of those drumlins, the pointy end tells you the glacier was going this direction in this place. And once again, those are just erosional features by having a boulder stuck in the bottom of the glacier grinding out soil as it travels. Okay. Finally, the work of air. I think this is the only slide I have on the work of air. I may be wrong. Air is also a major component of eroding and transporting material. You can have, the erosion and weathering both done by air. How a sand dune is made is interesting to me. You have wind blowing, the wind blows and it carries sand. So it carries that sand, you come to a little bump, it goes over the bump, and then you see the air starts to tumble when it gets to the other side of the bump. And because of that tumbling, it starts dropping sand out. And so you start building up layers of sand on the downwind side of that bump. And so as you keep going, you build up more and more on the downwind side, making a bigger and bigger sand dune. Of course, the same is true if you look at ripple patterns in water. It does the same thing. And on a similar note, if you drive on a gravel road and you start to form a rut, or not a rut, but a line that's perpendicular to the direction your tire is traveling, you'll start to form this kind of structure and make a washboard feature on your gravel road. So wind is also a big shaper of the surface of the earth. So if you go to, I went to graduate school at Washington State University, and out there in the Palouse, we have these wavy hills, if you will. And those were built by exactly this, by air blowing debris and building dunes that have now become wheat fields. the vegetation now holds the soil in place so it doesn't move anymore. Okay, another, No, I don't want to install software in the middle of class, surprisingly enough. You can answer now. There are many erosive agents that sculpt the Earth's surface. Overall, the erosive agent that does the most work is... Jocelyn and Raquel. It's an opinion question, Jocelyn. You don't have to look it up. Okay, so we had 4193. So we had a majority of people who said running water. Somebody wanted to explain why they said running water? Brandon.
Well, you said wind was the least effective. I'm pretty sure. Right?
I don't remember saying that. The slides, okay, yeah.
Sorry.
I was going to say, I do believe that's correct, but I don't remember saying it.
And groundwater, I think it's just like still water, so it doesn't move too much. And then glaciers, well, I thought that glaciers weren't all over the world, so I thought that they wouldn't do the most work. And so, and then running water generally cuts through stuff a lot.
Okay, now he answered every one of these. I was going to call a different person for each one, but he answered all of them, so I won't call anyone else. And he did a great job. Yeah. Groundwater, the stuff that's underground, does it do erosion? You bet it does. The whole sinkhole things were caused by groundwater, right? So it does, but not nearly as much as running water on the surface, because it's generally going to be running a lot faster. And then we have wind. Wind definitely makes an effect, right? You can't go to some town in Nevada that's been abandoned for 50 years and say, looks just like it was when they left, because it doesn't. The wind has made a lot of differences. And glaciers cause massive effects where they exist, but where they exist is more localized than streams, hence the running water. But, it was more of an opinion question, like I said to Jocelyn. I wanted you to think through these things and say, this is what makes sense to me, even though, yes, there technically is a correct answer. I wanted you to think it through. Okay, so I had two slides, one that was a question on air. Now let's get to geological time. So we've already talked about radiometric dating. We learned about half-lives and how that works. Radiometric dating is really important when we talk about geological time, because it's the cornerstone of how we identify how old things are. So with radiometric dating, we have some fundamental assumptions. Fundamental assumption number one is that the half-life of a material is constant always. Of course, with these assumptions, you need to have some reason to say, is that a good assumption or a poor assumption? So how can we know if that's a good assumption or a poor assumption? Yeah, we start with the assumption that the half-life of a radioactive isotope, let's say the half-life of carbon-14, is the same at all times, at all places. And we have a term for this, it's called universality. How would we justify that assumption? How could we, what lines of reasoning could we use to say it's a good assumption or a poor assumption? Observing what? I mean, we can't observe all locations or all times. We can only observe locations on Earth and right now. But what methods, how would you do that? Because obviously observation is a key in science. Okay, take samples from other places. Now here's experimentation that's actually been done that's along the lines of what Brittany said. You take a radioactive isotope that's in a different chemical, right? So let's say you have carbon-14 as the, in methane, and then you have carbon-14 in benzene. You're in a different chemical situation, you have different chemical bonds. According to conventional theory, that should make no difference because it's just what's going on in the nucleus, pretty much immune to what's going on out there in the electron cloud. Well, the research actually indicates that the half-life does change slightly depending on the chemical structure. So that says, oh no, the assumption does not perfectly ring true. Now, the next thing is how big is that variation? And that variation is actually really small. And so because the variation in half-lives that they measured depending on chemical composition was very small, the conclusion is it's still a roughly true assumption. Now, that's only checking locations, right? It's not checking times. We can't check what the half-life was a billion years ago. We can't check what's going to be a billion years in the future. So that is pretty much a blind faith idea, but it does have some backing based on our understanding of physics, our understanding of what causes radioactive decay to begin with. But it's not something that can be, proven. It's an assumption. So radiometric dating is how we date the rocks. Now, I, for better or for worse, like to read and occasionally participate in some creationist Facebook groups. And so recently, I've been participating in one that was talking about carbon-14. And the person started by mocking a false assumption. We call that a straw man argument when you say, oh, they believe this, but it's demonstrably wrong. Since they don't believe this, your argument's not valid. In this case, it was saying that scientists believe that the amount of carbon-14 in the atmosphere has always been the same. I believe I told you in class, right, that the carbon-14 in the atmosphere changes dramatically based on things like when you have a volcanic eruption, completely changes. And so that's not an assumption made in carbon-14 dating, right? It's just not. There is the assumption of constant half-life, but not the assumption of constant amount of carbon-14. But in this conversation, when I point out the flaw there, because that's what I do, I poke holes, somebody mentioned another thing that really is meaningful, especially to me as a creationist. Dinosaurs. One of the things we're going to get to is dinosaurs. Dinosaurs lived in what we call the Mesozoic, the middle era. Those dinosaurs were 60, 70 million years ago that they lived, according to radiometric dating. Well, sometime about a decade ago, somebody discovered that it looked like there might be biological cells, like proteins maybe, still available in dinosaurs. According to every theory of science, after millions of years, there should be absolutely no organic material, nothing left of proteins or blood cells or anything like that. It should all be gone. It should just be deteriorated. And yet they found some. And so initially, nobody even wanted to test it because they were like, well, that would be stupid. It'd be a waste of our time. It can't be biological tissue. But finally, some brave souls did. And they found, indeed, there is biological tissue in these dinosaurs. They're supposed to be 65 million years old. And then people said, well, why don't you carbon-14 date the dinosaurs? Why would you never carbon-14 date a dinosaur? The half-life, and actually, let me just go to, I think it's the next slide. Nope. I've got it here somewhere. There. The half-life of carbon-14 is 5,700, well, this says 60, 5,730 years. After about 10 half-lives, you have less than 1,000th of what you started with, and there's so little carbon-14 in the atmosphere that in theory, after 10 half-lives, you have a higher chance of no carbon-14 than you have a chance of finding carbon-14. And so they're like, okay, so 10 half-lives, that's like 60,000 years. So why would you ever carbon-14 date something that's older than 60,000 years? You shouldn't find anything. But finally, once again, people say, well, have you actually checked? And they did, and they're finding there's still some carbon-14 in these dinosaurs. And so that casts a whole lot of doubt into the dating, because we say that they're 65 million years old. They're 65 million years old, and they haven't been exchanging gas with the air, then there should be absolutely no carbon-14 in them. And so right now, those of us who are creationists are really taking a critical eye saying, there's something we're not understanding. So I want to make sure that you do know that this is not a closed book. The science is not absolutely true. There are questions there. Now, there are other things that make it look like a short age creation belief is not correct. And so we're going to be looking at the scientific interpretations, which starts with a fundamental, this is today, not, in Einstein's day, it was not the case. But today, science starts with a fundamental belief in what we call uniformitarianism. That's this slide. Uniformitarianism is the assumption that the Earth's geology is the result of slow processes over long periods of time, and assumes that natural laws have been constant throughout geologic history. Basically, it says that anything we see when we look at old rock should have occurred by a method that's occurring today, and that we just have a lot of slow changes. Now, for people who are young Earth creationists, they don't buy into uniformitarianism. They say, okay, so that is the glass through which you're looking at the data. But I'm looking through a different glass, and this glass says that there can be cataclysmic events. There could be something like a worldwide flood. And if you have a worldwide flood, you're going to have things that occur very rapidly. You'd have large-scale erosion, large-scale depositions, very rapid changes. And so creationists tend to take a point of view that says, number one, there could be a miracle. That is, God could create a worldwide flood. And in such a situation, we're still going to follow the known laws of physics of what would happen, but we're starting with, okay, so a miracle occurred. And the scientific approach, the naturalistic approach as we call it, says no, there cannot be a miracle. Everything has to be explained by nature, no supernatural. And so because they start with a worldview that says there can't be a miracle, there's no way that their outcomes are going to be, and a miracle occurred. Whereas the creationists start with a worldview that says there can be a miracle, and then they look at the outcomes and they find outcomes consistent with that miracle occurring. So you find a different result depending on which view you start with. It's an important thing to keep in mind. None of us have completely open minds. We come to everything with a certain preconception. And we're more likely to try to find stuff that fits our preconception than stuff that opposes it. Question, Jocelyn?
Are those the only two methods of dating rocks?
Okay, this here. The first method, the relative dating, is a way of saying, okay, this is older than that. We have a principle of original horizontality, which I think is, it's the next one here, yeah. The original horizontality says that it only makes sense that sediment formed in lake bottoms, and lake bottoms tend to be flat. So when we look at sediment layers, we should have the layers formed horizontally with the ones underneath older and the ones on top younger. That's a very reasonable interpretation. And so the relative dating of the rock is based on that. If I find this rock in the layer underneath that rock, then the one that was higher is younger, the one that was lower is older. That's what relative dating is. The other one, radiometric dating, radiometric dating is what we've talked about. That gives you an actual date rather than just older or younger. And so they're not really competing. The radiometric dating gives you numbers. The relative gets you younger and older. So when we look at the geologic column, the geologic column is if you dig down through the earth, you're going from higher level to lower level. So typically that should mean you're going from what age to what age? Going from younger to older. And so when we look at that geologic column, we assign, okay, this is the oldest at the bottom, this is the youngest at the top, and we don't have to assign a number date to it. We don't have to say this was 542 million years ago. We say this was a long time ago and this was less. And of course, creationists are very happy, generally speaking, with that. It's with putting the actual numbers on that you get with radiometric dating that creationists start to balk at. Okay, I skipped. These two slides tie together. As determined through radiometric dating, as well as our understanding of how the sun works and looking at the stage the sun is in, scientists determine that the age of the Earth is somewhere around 4.5 to 5 billion years in age. I say somewhere around because you'll see later on we have 4.55 billion years as a number, somewhere around that. And what's really interesting in looking at the history of the Earth as determined through the scientist viewpoint, that there is no God viewpoint, is how recent human history is. If we were to assign the entire history of the world as 1 year, then humans arrived on December 31 at 11:50 p.m. And that's not humans like you and me. That's the first of all hominids. Or hominins is what it says on my slides here. The Homo sapiens. We are Homo sapiens sapiens, right? So we are like brand new to the global scheme of the Earth. And so this picture, which I lifted from Wikipedia, is showing the history of the Earth kind of like a clock. So here is the beginning of the Earth. You see it says 4550 MA. M is million years, A is ago. So that's 4,550 million years ago, or 4.55 billion years ago. And then you have the formation of the moon very soon thereafter. We're not going to go into how the moon formed. Heavy bombardment. In the early stages of the universe, of the solar system, the theory is that we had chunks of matter coalescing together. And so you form this ball of Earth, and you have a bunch of other balls that are out there. And if one of those balls hits the Earth, big catastrophe, right? That's what the bombardment is. Different pieces of debris hitting the Earth. And so for this period that's called the Hadean, it was like Hades, like hell. You had large bombardment, lots of things hitting the Earth. But as you might recognize, each time something hits the Earth and gets absorbed by the Earth, that's one less thing that can strike the Earth. And so the rate of bombardment drops over time. And so heavy bombardment ends means that, well, you have a lot less. These days, we get hit by house-sized debris about once a month, right? So it's not that rare, but it's not like big chunks all the time. It's surprising. The Earth gains like millions of kilograms every day from debris hitting the Earth. Is that crazy? Of course, the atmosphere protects us. Okay, then we have Archean, very old time. And in this Archean period is when you have the first living things showing up. Then you go through the Proterozoic. Proterozoic is where you have eukaryotic things that have they have mitochondria, they have multiple cellular organisms, start showing up in that Proterozoic. And then you have a big event that occurs here. This says 541 million years ago. Depends on which years you look at, if it's 541 million, 542 million, 543. But you have the Cambrian explosion where suddenly we go from having maybe some little buggy things, trilobites, to having lots of different kinds of fish. And then you go through the Paleozoic, developing fish and some land creatures. Then you get to the Mesozoic, which is, as I said, the age of dinosaurs, the Middle Age. Meso is middle, Paleo is old. And then you get the Cenozoic, which is the recent. And so humans come in, the hominins. Yes, I said homonym instead of hominin. The hominins occur, that little tiny brown thing that you can't see, starting 2 million years ago. That's when things like humans appear. And we'll pick up with that, yes, on Wednesday.